Today we're going to finish our discussion of the physics that we kind of need to understand before we learn about astronomy, and we're going to talk about light. So far we've focused on how things move and why things move the way they do, and now we're going to talk about the physics of light, and we'll see why that's important as we go forward. Okay, so we're going to be talking about light today, and specifically light is electromagnetic waves. And the reason that light is so important is that's until the last 50 years or so, all of the information we were getting from space was in the form of light. So it's very important that we understand how light works if we want to study astronomy. Just a quick review of some of the rotational stuff we talked about last time. For every linear term, like position, velocity, or acceleration, there's a rotational version, which would be angle, rotational velocity, and rotational acceleration. You can use the kinematic equations the same as you did for linear motion and just replace all the linear terms with angular ones. And then once we saw a little bit of the physics of how things rotate and move in circular motion, we were able to derive the modifications that Newton made to Kepler's laws. So this is Kepler's third law, but modified to apply it to any two orbiting bodies, not just some object going around the sun. And you can also simplify the total orbital energy that an object has into just one term. So we ended last time talking about how you can change your orbit. And so which of these is not a way that you could change the orbit of a satellite? Yeah, so there were three ways that you could change something's orbit. Tidal forces are one way, so we talked about how the moon is tidally locked to the Earth, and that's causing the moon to slowly drift away from the Earth. So tidal forces are a way you can change orbit. If something else that has a lot of mass comes close to your orbit, then it'll pull on you with its gravitational attraction and alter your orbit a little bit. Or you can increase or decrease your orbital velocity, and that can either take you to a wider orbit or a narrower orbit. So the only thing that won't change your orbit are internal forces. So you need an external force to act on you, and anything happening inside of your spaceship won't change how you're orbiting. So we're going to start talking about light today, and we'll finish talking about light next class. So we'll talk about what light is, and in talking about what light is, we need to talk about what matter is and how those two properties interact with each other. So what is light? The first way that we'll talk about light is as an electromagnetic wave. A wave is a type of phenomenon that has some vocabulary associated with it. If I take a rope and I wiggle it up and down, then the distance between the peaks of my wave is called the wavelength. The frequency is how many times this motion happens per second or in some amount of time. The speed at which, so if you were to have a video playing, this peak wouldn't necessarily stay in one spot, it would travel along the rope, and that speed of propagation is the speed of the wave. And since we're talking about light in this instance, that speed is called the speed of light, and that has a very specific velocity that we'll talk about in a little bit. So waves are just are a phenomenon of something either oscillating back and forth, or in this case up and down, and that oscillation causes a velocity or a motion perpendicular to the oscillation. Wavelength is the distance from peak to peak. If I decrease that wavelength, then my wave becomes compressed, and if I decrease my wavelength, I increase my frequency. So the two things are inversely proportional to each other. It turns out if you multiply the wavelength times the frequency of a wave, then you'll get the propagation speed of that wave. And so for light, the speed of light is a constant. And so I just need to know either the wavelength or the frequency, and I can calculate the other one by knowing the constant speed of light. Or you could do an experiment where you're measuring the wavelength and the frequency of light and use that to calculate the speed of light. Here is the entire electromagnetic spectrum going from the shortest wavelength light, which is gamma rays, up to the longest wavelength of light, which are radio waves. So if we start from highest frequency or shortest wavelength, we go gamma rays, then a little bit longer wavelength, which means a little bit less frequency, are X-rays. A little bit longer wavelength than that, we get ultraviolet. A little bit longer wavelength than that, visible. Increase the wavelength more, we get infrared. Increase wavelength more, we get microwaves. And then the longest wavelengths will be radio. And so here are the kind of typical lengths that you would associate with those wavelengths. For radio waves, you're in the meters to tens of meters to hundreds of meters. But you very quickly get very small wavelengths from there. So microwaves might be in the realm between a pinhead and a baseball. Infrared, you're looking at animal cell size for one wavelength. Visible, you're getting towards bacteria. Ultraviolet, protein size. X-rays, you're in the atomic regime. And then gamma rays are even smaller than atoms. And frequency is just inversely proportional to wavelength, so the higher frequencies are on the left side and the lower frequencies are on the right side. What's interesting is we can actually tie the wavelength and the frequency to energy. So the higher frequencies have higher energies associated with them, and the lower frequencies have lower energy. But that means that higher wavelength is associated with lower energy. So wavelength and energy are inversely proportional to each other. So where you might encounter these different wavelengths on Earth, gamma rays, you're looking at some kind of radioactive material. We use X-rays to check inside of the body for broken bones, or I think here maybe they're looking for some kind of lung fluid. Visible wavelength light, obviously we use that in our interior lighting, and that's how humans see best. People actually emit infrared wavelength light. In the microwaves, we use things like radar and microwave ovens to cook our food. And then a lot of our telecommunications is done with radio waves. So humans have figured out a way to harness pretty much all of these different forms of electromagnetic radiation to do something useful. In astronomy, there are also a lot of different sources for these different wavelengths of light. So there are certain types of galaxies that are very strong emitters in the radio. The cosmic microwave background is basically a baby picture of the universe, and that's in microwaves, so we'll come back to talking about that later this semester. Planets and star-forming regions are not hot enough to do nuclear reactions, but they are warm enough to emit infrared light. The sun emits the most of its light in visible wavelength light. For things like ultraviolet, there are some ultraviolet emissions coming from the sun. X-rays can come from binary systems, and we'll talk about those later in the class. And then gamma rays, which are the highest energy, come from what are called gamma ray bursts, and those are the most violent explosions in the universe. And so this is part of my research, and so we'll talk about gamma ray bursts later in the semester. So it's important to understand the physics of light so we can talk about all of these astronomical sources. Light is a wave, but it's also a particle. So this gets into wave-particle duality, which is a consequence of quantum mechanics. So if you want to go a deeper understanding of that, you can take some upper-level physics classes. So particles of light are called photons, and those photons have the properties of a wave in addition to acting like a particle. So photons have a wavelength and a frequency, and the energy of that photon or that particle depends on its frequency or its wavelength. So a photon you can think of as a little point of energy, but so when that little point of energy hits something, it acts like a particle, but as it's propagating through space, it acts like a wave. So this is the relationship between wavelength, frequency, and energy. So we said earlier that if you multiply the wavelength, which is this Greek letter lambda, times the frequency, then you get the speed of light, c. And that speed of light is 3 times 10 to the 8 meters per second. In a vacuum, we'll talk about how light behaves in other mediums in a second. If you want the energy of a photon, you take the frequency and multiply it by this constant h. H has these weird numbers, and this is the Planck constant. So this formula is where you start getting into the quantum nature of light and it acting like a particle. And I guess it's not on this slide, but there's another formula for the energy of a photon. And it's just combining the two equations that we have on the screen. So we have lambda times frequency equals speed of light, and we have energy equals h times frequency. If we want the energy in terms of the wavelength instead of in terms of the frequency, we we can just solve this equation for frequency and then plug it in to this equation for frequency. So you get the energy is hc over lambda. So the question might ask you, what's the energy of a photon? And they might give you the frequency, and then you use this equation, or they might give you the wavelength, and then you need to use this equation. So if I want to increase the energy of my photon, how do I do it? Do I need a longer wavelength, a shorter wavelength, or is the photon energy not related to wavelength? Okay, so yeah, the equation that I just showed on the board, the lambda was in the denominator. So if I increase my wavelength, then I decrease my energy. Or if I decrease my wavelength, then I would increase my energy. So energy and wavelength are inversely proportional. The more accurate value for the speed of light is not quite 3 times 10 to the 8 meters per second. It's more like 2.9979 times 10 to the 8 meters per second. For any calculations you're doing in this class, you can just do 3 times 10 to the 8. That'll be the easiest. But we actually need to include these extra digits when we're talking about comparing the speed of light in different materials. So it turns out when people say the speed of light is a constant, they mean the speed of light traveling through a vacuum is a constant. As soon as that photon goes from vacuum, say you have a photon traveling from the sun coming towards the Earth, when it's traveling through space, the speed of light will be the speed in the vacuum, and then when it hits the Earth's atmosphere, now the light is going to slow down a little bit, and now it's going to be 2.9970 instead of 2.9979 times 10 to the 8 meters per second. So the speed of light changes depending on what medium it's traveling through. And then if that photon, let's say it went all the way through the atmosphere and then it hits the ocean, once it enters the ocean, it slows down even more to now 2.25 times 10 to the 8 meters per second. So the fastest that the photon will ever travel is in a vacuum, and then through different types of material, the speed of light will change depending on that material. So this has some interesting consequences. One of those being Cherenkov radiation. So this is an astronomy application for understanding the speed of light and how particles that travel that fast behave. So we've said that the speed of light in a vacuum is the fastest that something can travel. There are particles that also travel at that speed, but they actually travel faster than light travels in air. So let's say we have a photon starting in space and some other high energy particle traveling through space. They both hit the atmosphere going the same speed, but because of the way that light interacts with air, the photon slows down, but that other high energy particle doesn't slow down when it hits the air. So now I have a particle that's traveling, or it doesn't slow down as much as the photon does. So now I have a particle that's traveling faster than the speed of light in air. Physics doesn't like that. So because that particle that cosmic radiation was not, didn't slow down as much when it hit the air, there is another mechanism that will cause that particle to slow down, and that's called Cherenkov radiation. So basically, that high energy particle that didn't slow down as much when it hit the air will start to radiate photons. So these are blue light that's being emitted. That faster than light particle emits these Cherenkov photons, and that causes the particle to slow down so that it matches the speed of light traveling through air. So yeah, this is pretty cool physics. You have to get into very high level physics to understand the math for this. But we have designed telescopes that look for this Cherenkov radiation. So these are telescopes in Arizona. I worked on these one summer. This is called the Veritas array. And so they basically just look up at the sky and are always searching for these Cherenkov photons. And when they detect them, they can do some very high level physics to, let's say if I detect a Cherenkov radiation at this part of the sky, they can basically reconstruct the path of that Cherenkov radiation to determine what part of the universe that high energy particle originated. So this is just one consequence of the different speeds that light travels through different mediums can have impacts that you can study and use those to study things in space. The other more down-to-earth example that you've probably seen is called the index of refraction. And this is what causes, say, a pencil in a glass of water to appear that it's bent or broken at the interface between the water and the air. So this is a consequence of the speed of light through the water being different than the speed of light through the air. So the speed of light through the different mediums is related to what we call the index of refraction. That's what the lowercase n is. And so you can get a difference in angle between different mediums, and that causes this pencil to look like it's broken in the center. Just a consequence of the different speeds that light travels through the water and through the air. Okay, so that's a brief overview of what light is and how we study it. And the other important thing for astronomy that we'll talk about is matter. So matter is all the stuff that you're made out of and that the Earth is made out of, everything that's made out of atoms, basically. So an atom might look something like this, where there's a very dense nucleus made out of protons and neutrons, and then there's a cloud of electrons that are bound to that nucleus. So there's a very dense center that's positively charged, and then there's a very diffuse cloud of electrons that are negatively charged. But the total charge on the atom is usually going to be neutral. And atoms are very small, so that's 10 to the minus 10 meters across. There's some important numbers that will make talking about different atoms easier to do. The atomic number is the number of protons inside of a nucleus. So hydrogen has 1, helium has 2. That corresponds to its number on the periodic table. The atomic mass number is the number of protons plus the number of neutrons. So this hydrogen is just a proton by itself, so it has an atomic mass number of 1. This helium has 2 protons and 2 neutrons, so it has a mass number of 4. Carbon has 6 of both protons and neutrons, so it has an atomic mass number of 12. The electrons have very, very small masses compared to the protons by like 4 orders of magnitude, so you don't really need to add up the number of electrons. Have different mass numbers that are associated to the same element. So for example, this carbon is carbon 12 because it has 6 protons and 6 neutrons. But you can have other carbon isotopes that have additional neutrons. So carbon 13 has 7 neutrons, and carbon 14 has 8 neutrons. You can't change the number of protons. If you did that, you would be changing the element itself. So adding a neutron to carbon just gives you a different isotope, but if you added a proton to carbon, you would get nitrogen. So those elements that have different mass numbers, but it's the same element, are isotopes of each other. And then in chemistry, you're not just stuck with having atoms by themselves. They can join together and make molecules, and we'll learn about some important molecules for astronomy a bit later in the semester. And the little subscripts, so if the number is at the top, they're talking about the mass number. If the number is a subscript down below, then they're talking about the number of atoms that are in that molecule. So H2O has 2 hydrogen, 1 oxygen. CO2 has 2 oxygen, 1 carbon. So if you are interested in how those atoms form molecules, then you can take a chemistry class. Okay, so there's light, electromagnetic radiation, there's matter made out of atoms, and those 2 things will interact with each other in various different ways depending on the photon and the material that it's interacting with. So there can be emission. So this is where the matter will change its configuration in such a way that it emits a photon. Matter can absorb a photon. Photons can pass through or be blocked by materials. And then there are special types of way that light will bounce off of objects called reflection or scattering. So this is just a diagram of all the different types of ways that light and matter can interact. So the sun is emitting light, and that's coming towards the earth. This lamp is also emitting light. The light can reflect off of a mirror and be seen by your eye. There's also light that's coming from the lamp and hitting the chair. That light is then diffracting off of the chair and spreading out into the room, and some of that red light is bouncing off of the chair and hitting your eye. Some of the light from the lamp is also being transmitted through the window. Some light from the sun is reflecting or refracting off of the snow, but some of it is being absorbed and heating up the snow. So lots of different ways for light and matter to interact. For reflection, if you have something like a mirror, this purple light is a light ray. Light ray has some incident angle onto the glass, and when it's reflected, it will bounce off at that same angle and go out the opposite direction. Something like a screen, like at a movie, or this screen that we're looking at now, will, if you have a projector, that projector is sending photons towards the screen. Those photons are scattering off of the screen, and so everyone at the different seats in the theater can see the same image on the screen. If everything was perfectly reflected, then not everyone in the theater would be seeing the same picture on the screen. So different applications will call for different types of reflection or scattering. So light is a form of energy. We can think of it as an electromagnetic wave, or we can think about it as a particle called a photon. And we talk about photons by talking about their wavelength, frequency, and energy. There's all of these things are light: radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays, but they have different wavelengths, and they will behave differently depending on what they're interacting with. And matter is made out of atoms, which are made out of protons, neutrons, and electrons. And light and matter interact in several different ways. So if we want to start asking questions like how will we use this knowledge of light to talk about astronomy? So one of the ways that we can use light is by is to study the temperature of objects. So in this example, I'm bringing a fireplace poker near a fire, and before I get close to the fireplace poker is just its normal color, which is black. As I bring it towards the flame, it starts to heat up, or its temperature increases, and it starts to change color. So when it's just starting to heat up, it's more of a red color, and then as it gets very hot, it turns from being red to being a white color. So the temperature of an object is related to the color that we will see from that object. So everything that has a temperature associated with it is going to be emitting light. And the only thing that will determine the spectrum or the type of photons or wavelength of photons that you're receiving from that object is going to be its temperature. And we said that the temperature was the average kinetic energy of the particles inside of that object. So stars obviously emit light. That's where we get all of our light from the sun. Planets and you, we don't do our own nuclear reactions, but we do have a temperature, and therefore we're emitting some kind of photons. You could ask what kind of photons, and that will deal with what's called a black body spectrum. So here we are plotting the wavelength of light emitted by an object and the intensity or the amount of photons basically coming from that object. And we have here plotted 3 or 4 different curves. One for a star that has a temperature of 15,000 Kelvin, another for the sun that has a temperature of 5,800 Kelvin, another star that has then these are surface temperatures of 3000 Kelvin. And then this black curve at the bottom is the temperature for a human that has a temperature of 310 Kelvin. So the human is emitting photons, but they're at this wavelength, 10 to the 4 meters, or nanometers, which is in the infrared wavelength range. These different stars are emitting photons across a wider range of wavelengths, but the temperature kind of will dictate the peak of their emission and also how the highest energy photon that they can emit. So this 3000 Kelvin star does not emit as high energy photons as the 15,000 Kelvin star. And the peak of their emissions is also different. So these are called black body curves, and so anything that has a temperature will have a curve that looks something like this. Humans just have a very low temperature, and so we're not able to emit high energy photons like gamma rays, which is a good thing because we would all die if we did. So there's an equation for where this peak emission occurs called Wien's law, and you just take this constant 2.9 times 10 to the minus 3 and divide that by the temperature in kelvins. If you do that for the sun, it turns out the peak emission for the sun is in the visible spectrum. So which of the following of these has a higher temperature? Yeah, so between blue and red, if you look at the wavelength for blue, it is a shorter wavelength than the wavelength for red, and so shorter wavelength would imply higher energy, which implies higher temperature. So when we start talking about different types of stars, it'll be the blue stars that are bigger and have the most energy, and red stars are going to be smaller and have lower energy and lower temperatures. So all of the stuff that we've talked about so far with light has been what if things are stationary and nothing is moving. But we've seen when we talked about how the Earth moves, the Earth spins on its axis, it orbits around the sun is moving through the galaxies are moving away from each other, so nothing's ever really stationary. And so there's some interesting physics for how the frequency of a wave changes depending on how the object is moving. So this is called the Doppler effect. And so we'll have an example where we have a siren moving, but you've probably experienced this. So if you have a siren or a train horn and the train is stationary, it has a specific frequency or pitch. If the train is moving towards you and blows its horn, you'll hear a higher pitch even though it was the same horn that made the sound. Or if the train is moving away from you, you'll hear a lower pitch or lower frequency. And so sound waves are different than light waves, but we have an analogous behavior for when a light source is moving. So a light source moving towards you will be blue shifted. So whatever light that's emitted from that source will be more blue. Or if the light source is moving away from you, then that light source will appear to be more red. And when we talked about how all of the galaxies seem to be moving away from us, that means everything in the universe, for the most part, is going to appear to be redshifted from our perspective. So here's an example. And so as soon as that fire truck went past you, you could hear a very clear change in the frequency of that sound. And so for light, object moving towards you is going to be blue shifted. An object moving away from you is going to be red shifted. And if the object is just kind of moving across your line of sight, then it's not going to be blue shifted or red shifted. What exactly it means to be red shifted or blue shifted will deal with what the spectrum of that light source looks like, and we're going to talk about spectra and how the characteristics of light when dealing with spectral analysis. We'll talk about that next class.